Alrighty, what's going on, my friends? As always, no matter where you are, I hope things are going fantastically well for you. Now, my name is Dr. Jason Dinsmore, aka the OChem Whisperer, and I want to help you succeed in your organic chemistry class. Now, what are we going to be going over specifically in this lecture? What we're going to do is try to figure out how to understand hydrohalogenation of alkynes. Not alkenes, but alkynes. So for those of you that have been following along and you've seen the alkene chapter, or the alkene lectures, it's going to be very similar. So what we're going to do is we're going to go over the reaction, we're going to take a look at the mechanism, we're going to find out that it is incredibly similar to alkene chemistry. You're going to find these similarities between alkenes and alkynes. So if you understand alkenes, then you're going to understand alkynes. All right, so let's start with this one right here. So what I want you to do is take this alkyne, and remember this is a terminal alkyne, and terminal means that you have a hydrogen on one side. So we're going to take this terminal alkyne, we're going to add HBr, but just one equivalent of it. And what I want you to do is predict, what do you think the product is going to be? So take some time, go ahead and pause the video, or if you're watching this live, go ahead and just work through it, all right? But go ahead and make sure you're working on this because that's what's most important, all right? All right, so I'm hoping that you took some time to work on this. So in terms of this, we want to look at this and we want to think about, just like we did with alkenes, Markovnikov versus anti-Markovnikov, we also want to think about that here with alkynes. So in this case, what we're going to wind up doing with one equivalent is we're going to add an H to the least substituted side, and we're going to add our Br to the most substituted side. So this is going to be our Markovnikov addition. But we'll notice here that remember when we did alkenes, we went from a double bond to a single bond? With triple bonds, what we're going to do is, there are cases if we use one equivalent. Now just one equivalent, we can go from the triple bond to the double bond, or the alkyne to the alkene, all right? Now, let's go ahead, and what's key here, I just forgot about this slide, what we always want to do is make sure that you number all of your carbons. And the reason this can be confusing is because you'll see in my starting material, I drew the terminal hydrogen, hydrogen on our terminal alkyne. Your professor may or may not draw that. And what can sometimes be confusing is when you see these three lines, there's a carbon on both sides of those three lines, that alkyne, and you want to make sure that you keep track of that because I've seen students forget to do that. I'm pretty sure I forgot to do that when I was taking the class as well. But just make sure you number all of your carbons so you can keep track until you get familiar with the fact that there is a carbon on both sides of that triple bond, all right? Now, let's go ahead and take this now. What would happen if we added two equivalents of HBr? Not one, but two. So go ahead once again and take some time and see if you can figure out, predict the product, what you think it might be, all right? All right, so I'm hoping that you took some time to do that because like I said, I want you to work out all the kinks here on these live lectures so essentially you're going to crush your class or your exam, whatever that is, okay? So we want to work out all the problems here so you feel completely comfortable going into your quiz, exam, whatever it may be. All right, so let's take this one equivalent at a time. So if we took this triple bond and we added one equivalent of HBr, what's great about that is we already saw it, right? We know we add an H to the least substituted side, we add our Br to the most substituted side, all right? So we're just going to do our Markovnikov addition across there. Now, what happens if we add the second addition? Well, you can check this out. You can kind of think about it this way. That's an alkene, and we're just adding HBr across the double bond. So we already know how to do that because we already learned that. So what's going to happen here is we're going to add our H to the least substituted side, and we're going to add our bromine to the most substituted side. So what's cool about this is you can see the fact that the bromines always go on the same side, the hydrogens always go on the same side. So if you know how to add one HBr, then you know how to add the second one, okay? And so we can see this is a Markovnikov addition. All the bromines go on the most substituted and all the H's go on the least substituted, all right? Pretty simple, right? If you're probably, the connections are probably being made and you say, well, this is just like alkene chemistry. Exactly, it's just like double bonds, all right? Now, what happens if your professor said instead of one equivalent and instead of two equivalents, what if your professor said excess of HBr, all right? What do you think's different there? Well, what you're going to find out is if your professor writes two equivalents or excess, it's basically the same thing. So what we're trying to convey here when we put this, whether it's your professor or I'm putting it here, is that you need two equivalents of HBr, at least two equivalents of HBr, in order to go from the triple bond all the way down to the single and use all those extra pi bonds on there, okay? So you need at least two equivalents. What your professor may do is put excess, just saying you have more than enough bromine, HBr, to actually do it and take it all the way to the alkyne, from the alkyne to the alkane, all right? These alkenes always get, when I say it, it gets kind of confusing. But yeah, so if you have an excess, it's saying, your professor's saying you have more than enough to actually take it and go all the way from the alkyne to the alkane, okay? But all you really need are two equivalents. So you may see two equivalents, you may see excess, but the products are going to be the same, all right? Now, let's go ahead and take a look at the mechanism and see. And you're going to find out this mechanism is incredibly similar, if not almost the same as the alkene chemistry, all right? So we have our triple bond, we have our HBr. We know that our triple bond or our alkene or our alkene or alkyne, whichever one we're using, we know that pi bond is electrons. We know those electrons can act as a nucleophile because nucleophiles essentially are a pair of electrons. So in this case, our double bond, or sorry, our triple bond, one of our triple bonds, can swing out and grab the H, and what that'll do is break our HBr bond, giving us this intermediate right here. We've added our H to the least substituted side, and then we've generated a carbocation on the quote-unquote most substituted side, all right? Now the thing is we'll just follow this out by things we've done before, so we know that we've just made a Br minus. That Br minus now can come in here. The minus can now attack the positive. We always go from nucleophile to electrophile, negative to positive, some sort of lone pair to a positive, and essentially we form that bond and wind up getting that. So we get our H on the least substituted side, and we get our Br on the most substituted side, all right? Now I'm not going to finish this mechanism out because if you have or you haven't watched, in those live lectures, I already do the mechanism of HBr across a double bond. So basically you can just follow this procedure that we did right here to finish the mechanism out, or you can rewatch the lectures that we did where essentially you just add that across there. But we already know that we're going to add the bromines to the same side. We're going to add H's to the same side. So go ahead, once again, just fill that out for yourself. I'm not going to go through it, but just kind of do it on yourself to make sure that this all makes sense, all right? All right, cool. Now let's go ahead and look at this. So let's say we have, instead of a terminal alkyne, remember terminal means we have an H on the end, but what if we have an internal alkyne, which means that on both sides there's carbon groups, okay? And if you're not really familiar with internal versus internal versus terminal alkynes, I'm just getting confused with all these terms today. You can always rewatch. I think I might have talked about it in the Introduction to Alkynes lecture, or it might be one of the ones thereafter, but it's somewhere in there. You should be able to figure out or learn about the difference between terminal versus internal. All right, so what's going to happen here? Now, what I want you to do is, we know that we're going to add the H to the least substituted side, and we're going to add our Br to the most substituted side. But if you look at this, there's no difference. So check this out. It doesn't matter which side you add. You can add your H, you can add your Br to the left side, your H to the right side, or you can add your H to the left side or your Br to the right side, okay? It doesn't matter since it's symmetrical. You basically are just going to add your groups on there, and then if you had two equivalents, you would just add your bromines to the same side, and you add your H's to the same side, all right? It's pretty simple, right? You can see that this lecture is not going to go very long because we've pretty much already done this with alkene chemistry, all right? All right, and with that, that's all I have. But until next time, I hope you all have a good one.